Hello, everybody. So in these videos, I'm going to now show you that linear transformations are matrix transforms and vice versa. We've always had that matrix transforms are linear transforms, but now I'll show you that every linear transform going from Rn to Rm is actually always a matrix transform, which is just a great result. It means that all those times in previous examples where I showed you that this one transform was actually a matrix transform and then a linear transform, is the preferred way to go about showing that a transformation is actually a linear transform. Just gotta show it's a matrix transform because matrix transforms and linear transforms, when the transform goes from Rn to Rm, is one and the same. They're exactly the same thing. What's really cool about the result, though, is not only can I show you that a linear transformation is a matrix transform, but I can tell you ahead of time what the standard matrix is. And it's really easy to find. So it says, suppose that T going from Rn to Rm, that's a linear transform. Then it has to be a matrix transform, and its standard matrix is found by just applying the transformation to the basis vectors, the standard basis vectors for Rn. And the results are the columns of the matrix. So the first column of the standard matrix is T applied to E1. The second column of the standard matrix is T applied to E2, and so on. So that's really neat. That's really neat. Showing you why it's true is also very easy based upon the things we already have. So what if then you wanted to prove this result? So suppose that X is some vector in Rn. We know, though, that if I take T of X, X though can be represented as a linear combination of the standard unit vectors in Rn, because E1, E2 up to En is a basis for X, or at least for every vector in Rn. But then we remember that T is a linear transformation, so it can distribute through all those vector additions and the scalar multiplications to get this. But then we notice that is a linear combination in Rm, and in Rm, linear combinations can be represented by matrix multiplication. It just happens to be that particular product. It's the product of the matrix I just mentioned to you times a vector whose components, whose entries are x1, x2, x3 down to xn. That's really, really neat. So it's really, really easy to prove too. Now, I think it's probably worthwhile to show this in action at least once. So I did projection upon the x-axis, but what if we want to do projections just upon a line, just a general line? Let's insist also that the line goes through the origin. If it doesn't go through the origin, this doesn't quite work out. There's more to do, but not much more actually. So I want to know, let's say that P sub L going from R2 to R2 is going to project points onto the line L, and that line L goes through the origin and it has a direction vector U. Also, just because it makes it easier, direction vectors can be any length, so let's just make it be a unit direction vector. If it's not that, we could always just take the direction vector you give me, take its length, and normalize that vector to get a unit vector in the direction of the line. So it's not hard to find this thing. So let's say that the vector U has components U1 and U2. I want to know then, where does P send it? Well, to do that, the theorem I just gave you, let's assume it's a linear transformation for now. Let's assume it's a linear transformation. If I assume it's a linear transformation, then it must be a matrix transformation, and the columns are this transformation applied to E1 and this transformation applied to E2. Those are the first and second column of this matrix. So I'll just take the projection of E1 onto the line, which is onto the vector U. We've already done that projection computation before. It's as you see it right here. But in the denominator, you have U dotted with U. That's the length of U squared. But the length of U is 1. So squaring it is 1. That means you get that computation. But I know what the vector U is. It's just U1, U2. So I can do the dot product of that with E1. I give you that. There you go. That's the result of projecting E1 upon the line, because that's essentially projecting E1 upon U. You can do the exact same thing for E2. I'm just going to skip through the computations. Just give you the answer. That means that I know the standard matrix. The standard matrix is just these two columns. That's these two guys right here. Now, normally I would just say, and we're done. But there's other magical things we could do here. There's other really neat things we can accomplish because there's so much algebra power that we've gone and built up. It's not just numerical computation. We've gone beyond that in some cases. There's clever things we can do in order to write that multiplication a different way. Notice you can write it that way too. Think of the first column as a scalar times a matrix, a scalar times a column vector. That's scalar multiplication. You can put that scalar anywhere you like. I'll just put it back. But then I notice that when you write the vector this way, when you write the matrix this way, that looks like the result of matrix column multiplication. And in fact, it is. It's actually the matrix U applied to the vector in column and row form, U1, U2. But when you write the vector U1, U2 in row form, the original vector U was written in column form. So if I want the new vector, I have to write this guy. As the transpose of U. And that's it. That's the really neat thing about this result, is that if you want the projection upon a line, all you need is the unit vector. And then you write that unit vector as a row vector, that you write as a column vector, and you multiply it by the transpose of it. That will then be a 2 by 2 matrix. If you don't believe me, remember that this guy here is a 2 by 1. The transpose, therefore, is a 1 by 2. The result is a 2 by 2, as it should be. So that's a really neat result. Now, if you don't believe me, we can always apply it to something else. Earlier on, I showed you how to project something upon the x-axis. Well, the vector 1, 0 is a direction vector for that line. The x-axis is the line y equals 0, and that direction vector is 1, 0. So since that's a unit vector, I can take the vector 1, 0, take its transpose 1, 0, and just do this matrix multiplication, and you get the exact same standard matrix I gave you before. Isn't that neat? So you can always do this then with anything you like. Now your book gives you a harder, frankly, a more difficult formula. Your book actually does the same thing, but it does it with a direction vector where it's just D1, D2, and it's not a unit vector. And it writes everything in terms of components. So in terms of U1 and U2, and it's just a whole bunch of symbols all over the place. It's really not a good idea. The way I've written it here, that projection is the same as projecting upon a vector. If it's a unit vector, can be accomplished by a linear transformation whose standard matrix is U times U transpose. This is really much better for you long term. You'll see later on, because this idea of projection upon other things will pop up again, and that exact object will also pop up with it. It'll just be a sum instead of just a single product. Okay, so then the next things we want to discuss is if you have transformations, how can you make new ones? Well, these are just functions. So then because of that, we can just do compositions. So given a transformation that goes from Rp to Rm, and another transformation going from Rn to Rp, then you can find a new transformation, T composed with F, so T composed with S, that goes from Rn to Rm, which is a new transformation, which is just applying S and then following it by applying T. This notation you see right here, that's just normal, everyday boring function composition. Nothing new there at all. What is new though is what if both these transformations are linear transformations? Is the composition also a linear transformation? And yeah, and actually it's really obvious to see because since these are all going from Rn spaces, these transformations, if they're linear, they have to be matrix transformations. So then composition boils down to actually composition of matrix multiplication. The resulting thing will then be a matrix. And therefore, the resulting transformation would also be a matrix transformation and therefore linear. So without actually writing down the actual form of proof, given two linear transformations, their composition is always also a linear transformation. And if you want to know their standard matrix, you literally find the standard matrix of each separate transformation and just multiply it in the order that the composition is done in. And that gives you, again, a really super nice formula. That the standard matrix of the composition, T with S, that's what this side here says. the standard matrix of the composition is formed by taking the standard matrix of S, take the standard matrix of T, and just multiply them. And as long as the sets are mapped out correctly, notice that the codomain, notice the codomain of S is the domain of T. As long as that's true, then these two matrices will be of appropriate size so that you actually can do the multiplication. Now, I'm not really terribly interested in proving that, as it's in the book and I literally just spoke out the proof. I think it'd be better just to use it. So as an example, here are two transformations. So S goes from R3 to R3. T goes from R2 to R3. I want to know the standard matrix of S composed with T. Now, I notice I reversed the symbols. That's because to go from S into T, I have to make sure that the codomain of this guy has to be domain of that one. If I try doing it in the other order, this is undefined. We can't do the other order because in the other order, T composed with S would act first. So at S would then act on R3 and will give you back a vector in R3. But then T has to act on that next. If it's T composed with S goes first, then T follows. But T can only be applied to vectors in R2. And this vector here, that's not an R2. So T can't be applied to it. So T composed with S is not defined, but S composed with T is. So to figure out that particular thing, it's the standard matrix of S multiplied to the standard matrix of T. All I gotta do is figure out what those are. Notice you can write this as a linear combination. It's actually x1 times 1, 2, 1 plus x2 times the vector -1, 0, 3. So the standard vector, the standard matrix is just 1, 2, 1, -1, 0, 3. And that's multiplied to the vector x1, x2. So I know the standard matrix for T. Now, if you want to, you don't have to do what I just did. And instead, there is a standard matrix here. The standard matrix is S applied to E1, S applied to E2, and S applied to E3 by the theorem I gave you. And then you would have it multiplied by x1, x2, x3. So here, if I take this mapping and I apply it to the vector 1, 0, 0, you get the vector 2, 0, 0. If you apply the mapping to E2, that's 0, 1, 0, you get the vector 0, 3, 0. If you apply this mapping to E3, 0, 0, 1, you get the vector 0, 0, 1. And that means that we now have x1, x2, x3. We now have the standard matrix for S. So the standard matrix of multiplication of the composition is just it's 2, 0, 0, 0, 3, 0, 0, 0, 1. And then I multiply it by 1, 2, 1, -1, 0, 3. That's it. That's the standard matrix. That will then give you the mapping T composed with S composed with T. So if you want to know then, what is then S composed with T applied to the vector x1, x2, x3, I can instead just go ahead and take the matrices that you see here, 2, 0, 0, 0, 3, 0, 0, 0, 1, times 1, 2, 1, -1, 0, 3, and just multiply that by x1, x2, x3, and that matrix product will then give me the answer. That'll be the vector in R3 that is equal to. It's really neat, right? So then you can very easily figure out compositions. So let's try it out so you understand what I'm doing. I want this new transformation to first rotate a point 90 degrees counterclockwise about the origin, and then projects it upon the y-axis. So when I think of the transformation T, it's really a composition of two transformations. I first rotate 90 degrees and then I go and project it upon the y-axis. I want the standard matrix of that transformation. If I can find the standard matrix of the transformation, I know the transformation. So I need then the standard matrix for this projection. Well, for the projection upon the y-axis, that's just the line x equals 0. And it has a unit vector that describes it. That unit vector is just 0, 1. And well, at least in column form, not like that. I wrote row form. That would be in column form, 0, 1. So this standard matrix would just be, it'd be U times U transpose. That would be 0, 1 times the vector 0, 1. And that is 0, 0, 0, 1. That's then the standard matrix to project things upon the y-axis. Nice, right? You can check it too if you like. Just take P of y and apply it to xy. That's the same as taking the matrix 0, 0, 0, 1 and multiplying it by xy. And notice what you get is 0, y, which is on the y-axis. All right, so we have that one done. Next, what I need is I need the rotation. So I need the rotation to 90 degrees. Well, I just gave you a way to find that standard matrix though. That was the cosine of the angle. We're going counterclockwise, so it's 90 degrees. Negative the sine of 90. Then you have the sine of 90 degrees. And then you have the cosine of 90 degrees. So then these are all degrees, 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 and degrees. So we easily can find what that is. That's 0, negative 1, 1, and 0. So then if I want the standard matrix for this transformation, it's the standard matrix of this projection multiplied to the standard matrix of the rotation. So that would then be, I'd have 0, 0, 0, 1 multiplied to a 0, negative 1, 1, 0. And that, if you just wind up doing multiplication, you wind up getting 0, 0, and then you get we'll see, that'll be 1, and that'd be 0, and that's it. That's neat. So then that will do the option. That will go rotate it. It will rotate it 90 degrees, and then project it upon the y-axis. So if you want to know what is t applied to xy, that would then be 1, 0, 1, 0, 0, 1, 0 applied to xy, and that multiplication winds up being 0x. That's it. And that particular mapping I just gave you will first rotate things 90 degrees counterclockwise about the origin, and then it will project it upon the y-axis. Neat, right? So you can then see how we can use these ideas to simulate computer graphics very, very easily, to actually manage or do the computation end of computer graphics, as it's just transformations applied to other transformations and so on. Now, there's one more we need to talk about is if you have a mapping, sometimes you want to undo that mapping. So way back when in college algebra, you learned that two mappings are undo each other or inverses if their composition is what's called the identity element. So here we call the identity mapping I sub n. So that's not the matrix, that's a mapping. So that mapping will go from Rn, it will go into Rn, and the mapping is you give me any vector and I'll give it to you right back. That's the identity mapping. So then we say then two linear transformations, both from Rn to Rn, they have to be the same, going from the same domain, same codomain, and the domain to codomain must be the same. They're called inverses if you use the composition in either order and you get the identity mapping. So that's the normal definition of inverse functions. It's just slightly more ornate than you're used to. So we'd like to know then, if I have a linear transformation, how do we know it has an inverse? And then what would that inverse be? We want it to be really, really, really easy to figure that out because of, again, all the machinery built up. So then If you have a linear transformation that goes from Rn to Rn, we automatically know it's a matrix transformation. Well, then it seems pretty obvious that if the matrix has an inverse, then the transformation has an inverse, and the inverse transformation standard matrix is the inverse of the standard matrix of the transformation. So then that's the theorem. I'm not terribly interested again in proving it. It's not terribly difficult to do so. It's in your book if you want to go do it. It's really very, very obvious just from this thing right here, because if they are inverses, the standard matrix of this guy has got to be the standard matrix of the identity mapping. But the standard matrix of the identity mapping, since every vector gets sent back to itself, I can easily figure what that is because I just apply that identity mapping to all the standard vectors in the basis for Rn. So I apply to E1 is E1. I apply to E2 is E2. I apply to En is En. So the standard matrix is actually the identity matrix. But then we also know that the standard matrix of a composition is found by just multiplying the separate transformations, the separate standard matrices. But then we remember something else I proved, that if two matrices are both square and their product is the identity matrix, then those matrices are inverses of each other, and that gives the result that we actually need. So it's, and there's more to it, of course, but that's basically the proof. It's incredibly easy, and it's based upon things we already know. The important thing is, though, is that the transformation is invertible if and only if the standard matrix is invertible. And if it is invertible, you can very easily find the standard matrix of the inverse transformation by taking the inverse of the standard matrix. So the standard matrix of the inverse is the inverse of the standard matrix. It's really great. So I'll give you an example of doing it. Let's say that the linear transformation that reflects points in the x-axis, I'm going to show you that that thing is invertible. And then I'll show you the standard matrix of that inverse. And then I'll show you what that transformation actually is. It should be pretty obvious, but let's start off by assuming that this thing actually is a linear transformation, make our life a little easier. If it is a linear transformation, then let's figure out how it would map things. So if you want to draw a picture, it makes it easier maybe to see. Here is the vector that goes to x comma y. We're reflecting everything in the x-axis. So then that point goes down here. That new point would be x comma negative y. So this mapping has to be that it sends xy to x comma negative y. You have a choice now. If you want to find the standard matrix from here, you can think of it as apply the transformation to E1 and E2. Those are the columns. Or you can represent the actual image of the vector xy under R as a linear combination and then uncover the matrix multiplication. There's at least two ways. I will go with the standard matrix of R can be written as a matrix where you take R and apply it to E1 and take R and apply it to E2. So then doing that, R applied to E1 will just give you E1 back. Right? Oh, I didn't mean to put that other bracket there. So that's the first column. Second column, if I apply R to E2, that would then return back 0, negative 1. There you go. So that's the matrix. So but notice though, notice that the standard matrix is invertible. There's all kinds of ways to say that. One is because you can reduce this to the identity. So therefore, by the following are equivalent, it is therefore obviously invertible. Another is notice that by the determinant, A times D minus B times C, that product is negative 1 and it's not 0. So from a result I've already given you, this matrix, since it's determinants, this 2 by 2 matrix has a determinant, it's not 0, it has an inverse. I can even give you what the inverse is. So therefore, the original transformation is also invertible, is invertible. And if you want the standard matrix of the inverse transformation, it's the inverse of the standard matrix of the original transform. All I need, therefore, is the inverse of this matrix. Well, but if you notice this matrix, if you wind up multiplying it to itself, you actually get the identity element. You actually get the identity matrix. So then it winds up being that the inverse of the standard matrix is actually itself. It's the same thing. So the inverse that undoes this projection, if you apply it to the vector xy, can be found by taking the standard matrix for that inverse times xy. But we know that standard matrix, it winds up being the exact same matrix. And then by just doing the matrix multiplication, you get x comma negative y. And that then gives you the inverse transformation. So the last question then would be is, what is this inverse? And the answer is it's the same thing, right? Because it's the same mapping. The reflection in the x-axis is its own inverse, which makes sense, right? You reflect something, you can reflect right back. So they are inverses of each other. And this work then convinces you algebraically why it should be true. I think that's enough for this video. Good luck.